When we try to fit a linear model to a given data set, the idea is to find the line which best fits the given data. A line where the parameters are given by the intercept and the slope. We find the estimate of these two parameters by minimizing the error which is involved in fitting the linear model. In this module, we will discuss the mechanisms of such a technique where we minimize the square of the error which is involved in the linear model fitting, and we will see how we end up with the best fitted estimates of the coefficients or parameters involved in the model. So in this module, as I've mentioned in the introduction, we are going to look at the geometry of least square. When we try to fit a linear model to the data, the rationale behind fitting this model is finding the estimates of the coefficients or parameters involved in the model using the method of least square, where we minimize the square of the sum of errors. So here, before I start with the material, let me give you a brief outline of the mathematical basis of the matrix algebra that we are going to use in order to demonstrate the least square technique. First, the basics that we talk about are the inner or the dot product of vectors. If A and B are column vectors, then the dot product can be written as the summation of AI times BI, where AI and BI are the ith component of the vector. In case A and B are orthogonal, then the dot product or the inner product of the two vectors are going to be 0. In case of a matrix, if A and B are two matrices such that A has an order R times S and B has an order S times T, R being the number of row and S being the number of column for A and S as the number of rows and T as the number of columns for B, then A times B would be a matrix of the order R by T. Now talking of matrices, in certain cases, in order to find the least square technique, estimates of the coefficients, we need to partition matrices. So the basics of partition matrix are as follows. Partition matrix are like ordinary matrices, but the entries are matrices themselves. So if I have a 4 by 4 matrix, I can partition into 4 matrices of 2 by 2 order. They add and multiply just like regular matrices, but we have to remember that matrix multiplication is not commutative. So here is an example where we show two matrices A and B partitioned into 6 components. Think of A as a 2 by 3 matrix and B as a 3 by 2 matrix. Now we multiply them to get C, which is multiplication of A and B, and the final product will be a 2 by 2 matrix given as follows. But this only works if each of the matrix products in the formula makes sense. So A11, the first component of matrix A, must have the same number of columns as B11 has rows, and many other such similar restrictions will apply when talking of multiplication of matrices. So the first application of matrix partition is if we consider the design matrix in a linear model, X. This can be considered as a partition matrix, where each of the partition, which is xi, is a column of x, and xi stands for the vector values for ith independent variable. So then the product x times beta, where beta is the coefficients corresponding to each of the x's, can be written as the vector product of the partition matrix X and the vector beta 1, beta 2, beta p. So what we have is resulting linear form of, or a linear combination of the columns of X multiplied by the coefficients corresponding to each of them. So the form is beta 1 x1, beta 2 x2 plus beta p xp, which is a linear combination of the columns of X. Now the column space of X, we need to keep this definition in mind. So the column space of X, which is written as COLX, is the vector space of set of all linear combination of columns of X, also called the space spanned by the columns of X. So when we get the estimates of Y as X times beta hat, then the estimates all belong to the column space of X, which is the design matrix. Now moving on to the normal equations. We've already discussed normal equations which are used to estimate the coefficients of a linear model. So the normal equations are in the form x prime y equals x prime x times beta hat. Or when we solve for this equation, we get x prime multiplied by y minus x beta hat equals 0. Or we can write x as a partition of row vectors as x1 prime, x2 prime, xp prime, where each of these primes constitute the rows multiplied by y minus x times beta hat, which equals 0. So for each of these i's, we can write xi prime multiplied by y minus x beta hat equals 0, which means that y minus x beta hat is orthogonal to each of the vectors of the columns of x, because when we take the dot product or the inner product of these two, we were getting 0, as we can see in the previous step. Now, a very important and very common definition is that of the residuals, or the epsilon term, which appears in most of the linear models. So epsilon hat, which is the estimated error or residual, equals y minus x beta hat, is the fitted residual vector. So epsilon hat is orthogonal to the column vector of x, and epsilon hat is orthogonal to the estimated values of y. Now, according to Pythagoras' theorem, if we have two vectors which are orthogonal to one another, then the square of a plus the square of b equals a plus b whole square. By definition, a, as given in the above notation, is the length or norm of a. In case of a vector, the length or the norm of any vector a is given by the square root of the summation square of each of the components of the vector. Moreover, if a, b, c are all perpendicular to one another, then we can take the square sum of the length of each of them, which would equals the sum of each of them and the squared length. Now, the application of the above mathematical basics can be put to use in case of linear models. Suppose the y vector, which is the vector of response, is written as y minus x beta hat plus x beta hat. Now we've seen before that y minus x beta hat is the difference between the observed y and the estimated y. So that can be replaced by the error term epsilon hat plus mu hat, which is representing the mean value of y estimated by x beta hat. So the length of the vector y square equals the squared length of epsilon hat plus squared length of mu hat, because we have seen previously that they are all orthogonal to each other. So summation yi square equals summation epsilon I hat square plus summation mu I hat square, where by definition summation yi square is the total sum of square for the unadjusted values of the response. Summation epsilon I hat square is the error or the residual sum of squares, and summation mu I hat square equals the regression sum of square. Now, alternative formula for the regression sum of square can be found on the next slide as we derive them in terms of the x and the beta. So, summation mu I hat square equals the regression sum of square, which can be written as the dot product of the transpose of mu hat and mu hat. Now, mu hat can be represented as x times beta hat transpose x times beta hat, which translates into beta hat prime x prime times x times beta hat. Now notice that the matrix identity, which we will use regularly, is A times B whole transpose equals B transpose times A transpose, which is exactly what we have used in the previous derivation. Now, what is least square in terms of the geometry behind the technique of finding the estimates of the coefficient? What exactly is the least square? When estimating beta hat, we choose beta hat so that we can minimize the sum of square of errors, which can be written as summation yi minus mu I hat square. And in terms of length of vector, since y and mu are both vectors, we can write them as the squared length of y minus mu hat. That is to minimize the error sum of square. The resulting mu hat is called the orthogonal projection of y onto the column space of x, as we have demonstrated before. Now, as an extension, if we have two models, we can write them together, or if we have a whole model, we can reduce it to two partitioned models by using the technique of partitioning of vectors and matrices. Suppose X is the design matrix which we partition into two matrices x1 and x2, and we partition the beta vector as beta 1 and beta 2. So imagine there are two models. One is the full model where y equals x beta plus epsilon, and one is the reduced model where y equals x1 times beta 1 plus epsilon. So in the first model we have all the x's. In the second model, y is modeled on only the first set of vectors, which is the x1. If we fit the full model, we get the coefficients b f hat, mu f hat and epsilon f hat, where epsilon f hat is perpendicular to the column space of X. If we fit the reduced model, we get b r hat, mu r hat and epsilon r hat, where mu r hat belongs to the column space of x1, which is a subset of column space of X, because x1 is nothing but a part of the bigger design matrix X. Now we notice that epsilon f hat, which is the error from the full model, is orthogonal to the mu r hat, which is the estimate of the mean values of y for the reduced model. The vector mu r hat is in the column space of x1, as we have seen before by previous logic, so it is in the column space of X, and epsilon f hat is orthogonal to everything in the column space X. So we can write y equals epsilon f hat plus mu f hat, which equals epsilon f hat plus mu r hat plus mu f hat minus mu r hat, which in other words is epsilon r plus mu r hat. So we know that epsilon f hat is perpendicular to mu r, and epsilon f hat is perpendicular to mu f hat as well. So epsilon f hat is orthogonal to the difference between mu f hat and mu r hat. Also, mu r hat is orthogonal to epsilon r hat, which equals epsilon f hat plus mu f hat minus mu r hat. So 0 can be equated to epsilon f hat plus mu f hat minus mu r hat prime mu r hat, which is nothing but the dot or the inner product between the two variances, between the two vectors. So mu f hat minus mu r hat is orthogonal to mu r hat. So in summary, we have y written as a function of mu r hat, which is the estimated mean values from the reduced model, plus the difference between the estimated mean value of y between the full and the reduced model, plus the error term coming from the full model. So all three vectors on the right hand side are perpendicular to each other, which gives us the length of y square equals the sum of the squared length of all the vectors which are on the right hand side of the above identity, which is nothing but the analysis of variance table. If you remember, in the analysis of variance table, we have the sum of square due to the regression, the sum of square due to the residuals, and these two add up to the total sum of square, which is exactly what is represented by the identity above. So here is the most basic version of the model that we have just now talked about, the full model and the reduced model. Let us take X as a partition matrix where the first partition is 1, which is a vector of all ones, and we have the other part of the matrix which is x1. So the notation here is 1 equals 1, and it contains as many as the order of X matrix. So 1 is a column vector with all entries equal to 1, and the coefficient of this column is beta 0, which is nothing but the intercept term in the linear model. Now to find mu r hat, we minimize summation yi minus beta 0 hat square and get simply beta 0 hat equals y bar, or the mean of y, which is what we get when we find the estimate of beta 0 by method of least square. Also, mu r hat is a vector which contains only y hat or y bar, which is the mean of the y. So our ANOVA identity is now square of the length of y equals mu r hat square plus mu f hat minus mu r hat square plus the error from the full model square, which equals n times mean of y square plus the remaining terms on the right hand side stay the same. So this identity is usually rewritten with n times y bar square taken to the left hand side. So we have squared length of y minus n times square of y bar equals mu f hat minus mu r hat square plus epsilon f hat square. So remembering the identity, we find that summation yi minus y bar square equals summation mu fi hat minus y bar whole square plus summation epsilon f hat square. These terms are respectively called the adjusted or corrected total sum of square in ANOVA table, the regression or model sum of squares, and finally the error sum of squares respectively. In case of a simple linear regression model, we can use any one of the following as our response variable, which is a filled gas tank 107 times. We record distance since last fill and gas needed to fill. Then the question for discussion is whether we have a natural model that can be fitted into the model. So we look at the JMP analysis of the dataset. In the next example, let's consider a model Yij equals mu plus alpha I plus epsilon ij, where alpha 4 equals minus alpha 1 plus alpha 2 plus alpha 3. So the data consists of blood coagulation time for 24 animals fed one of 4 different types of diets. So each of these alphas correspond to 4 different types of diet. So now we write the data in a table and decompose the table into a sum of several tables. The 4 columns of the table correspond to diet A, B, C and D. We should think of the entries in each of the table as being stacked up into a column vector, but the tables save space, so it is easier for us to visualize the linear model. Now the design matrix can be partitioned into a column of 1s and 3 other columns corresponding to alpha 1, alpha 2 and alpha 3. So we first compute the product x prime x, which is the product we need to find the estimate of the beta or the coefficients, and we get the following matrix. So the matrix x prime y, which comes next, is calculated as follows. Now the matrix x prime x can be inverted using a program in R or simply using the function solve. So we have found the inverse of the x prime x matrix and it's given in the following form. It now takes quite a bit of algebra to verify that the vector of fitted values can be computed by simply averaging the data in each of the columns. That is, the fitted value mu hat is given in the table below for each of the 4 different diets. On the other hand, fitting the model with the design matrix, which is the X matrix, consists only of a column of 1s, just leads to mu r hat, which is given by the following table. Earlier we had seen the identity of y equals mu r hat plus mu f hat minus mu r hat plus epsilon f hat, which corresponds to the following identity. Because we have calculated these quantities x prime x and x prime y separately, we are able to write the above identity in the form of the matrix addition in the following form. The sum of square of the entries of each of these arrays are as follows. So keeping in mind the previous matrices, the uncorrected total sum of squares would be on the left hand side the square of 62 square plus 63 square and so on. The first term on the right hand side gives us 24 times 64 square. This term is sometimes put in ANOVA table as the sum of square due to the grand mean. But it is usually subtracted from the total to produce the total sum of square, which we usually put at the bottom of the table. This is often called the corrected total sum of squares in the ANOVA table. Now in this case, the corrected sum of square is the squared length of the table given in the next slide, which is 340. Now talking of the treatment sum of square, the second term on the right hand side of the equation has squared length given by 4 times minus 3 square plus 6 times 2 square and so on, which adds up to 228. The formula for this sum of squares is xi bar minus x bar whole square, and we have taken the sum over all the different observations which belong to each of the diodes, and also the sum has been taken over the 4 different diodes. So what we have in effect is sum over all the diodes Ni times Xi bar minus X bar square, where Ni stands for the number of observations belonging to each of the diodes. But what we want you to see is that the formula is just the squared length of the vector of individual sample means minus the grand mean, which is X bar. The last vector of the decomposition is called the residual vector, and it has a squared length given by 1 square plus negative 3 square and so on, and it adds up to 112. So corresponding to the decomposition of the total squared length of data vector is the decomposition of its dimension as well. We have 24, which is the dimension of the subspaces, which is further divided into the different sum of squares. For instance, the grand mean is always a multiple of the single vector, all of whose entries are 1. This describes a one-dimensional space. This is just another way of saying that the reduced mu r hat is in the column space of the reduced model design matrix. The second vector of deviation from a grand mean lies in the three-dimensional subspace of tables which are constant in each column and have a total equals 0. Similarly, the vector of residuals lies in a 20-dimensional subspace, the set of all tables whose columns sum to 0. This decomposition of dimensions is the decomposition of degrees of freedom as well, which is the third column in our analysis of variance table, next to the column for sum of square. So 24, which is the total dimension, is divided into or segregated into 1 plus 3 plus 20, and the degrees of freedom for treatment and errors are 3 and 20 respectively. So the vector whose squared length is the corrected total sum of square lies in the 23rd dimensional subspace of vectors whose entries sum to 1. So this produces the 23 total degrees of freedom in the usual ANOVA table. So in this module, we have learnt what is commonly known as the ordinary least square technique of fitting a regression model and obtaining the estimates of the parameters, namely the intercept and the slopes. So the mechanism here is to minimize the error which is involved in fitting the regression model and find that one line which best fits the given data.